Hello, ma'am. Am I audible to you?
Yes, sir. Good evening, sir. You are audible, sir.
Okay, ma'am. Thank you. Thank you so much. Ma'am, can I start the session now?
Sir, let's wait for five more minutes, sir.
Okay, ma'am. Okay, okay. No issues.
Sir, you can start now, sir.
Okay, ma'am. Okay. Good evening, students. So today we are going to discuss the concepts of electric potential. So already we have discussed the concepts of electric fields, Gauss law and all. Today we are going to continue with the remaining topics. So that is electrostatic potential. So that's what we are going to discuss today. So I am sharing my screen now. Are you all able to see the screen?
Yes, sir.
Okay, okay. Thank you so much. Thank you. So when we talk about electric potential or electrostatic potential, so first of all, we have to consider a source charge like this. Okay. So here you can see this charge plus Q. So let me consider this as a source charge. So this is a positive charge represented as plus Q. And this source charge produces an electric field around it that you all know very well. And what I am doing is I am bringing another charge plus Q prime, or this is also a positive charge and I am going to call it as Q prime. Okay. So I'm going to bring this charge Q prime in the field of this source charge. Okay. I'm going to move this charge. We can call it as test charge. So this Q prime charge, we are going to move it in the field of this charge plus Q. Okay. So now I am asking you a question. Is it easy to move this test charge in the field of this source charge? Is it easy to bring another charge, okay, in the field of this source charge? Is it an easy task? Anyone can answer. You can unmute yourself and you can talk during the session. Okay. So this is my question. Is it easy to move another charge in the field of this source charge? Is it easy?
No, sir.
Why?
Sir, because we need to, sir, we are bringing one charge uh,
Okay.
closer to another charge, sir, and both the charges are similar, so obviously there will be a repulsion, sir. So we need to do work against that repulsion to bring the charge closer.
Excellent. Excellent. Very good. Very good. So actually, this source charge produces an electric field around it, and since this is also a positive charge, okay, like charges repel each other. So due to the presence of this charge, the charge Q prime experiences a repulsive force. In other words, this source charge doesn't allow the test charge to be moved into its field very easily. So we have to do some work against the electric field of this source charge. Okay. So initially this test charge is at the point R, and I have to move this test charge in the field of this source charge. For that I have to do some work against the electric field of this source charge. So that work done is actually given by integral R to P F external dot dr. F external means the force which we are applying against the electric field of this source charge, that is called the external force. Okay. So here this integral gives you the total work done to bring the test charge from the point R to the point P. Okay, usually the work done is given by force into displacement. So here this is the force actually, and this is the displacement. So this entire distance between this P and R, it is divided into small segments of length dr, and when you integrate this equation with the limits R and P, you will get the total work done to bring this test charge from here to here, okay, from R to P. you will be getting the total work done. So this is the work done, and here actually what is the amount of work done to bring the charge to this point P? That work done is actually the potential energy associated with this point, okay? Because you are doing some work against the electric field of the source charge, and whatever work you are doing, it is stored as electric potential energy. So when you take this point R and you have brought this test charge from a point of infinity to this point R, so you would have done some work against the electric field of this source charge. So at this point R, whatever work you have done to bring the test charge to this point R, that work is stored as potential energy at this point R. And from here on, you are moving the charge further to this point P. So as you move towards the source charge, you will be experiencing more repulsive force. So you have to do more work against the electric field. Then only you can bring this test charge to this point P, because it is little bit nearer to the source charge compared to this point R. Okay. So whatever work you are doing against the electric field, it will be stored as potential energy at the point, and potential energy at point R is given by capital U suffix R, and potential energy at point P is represented by capital U suffix P. Okay. So the difference in potential energy between these 2 points, between this point P and this point R, is represented as delta U, and that is nothing but the work done. So that is given by this integral R to P F external dot dr. Okay. Now the next thing is, this F external is the work done by us, and as we have already mentioned, this work is done against the electric field. Okay. So here in this slide you can see the external work done by us is actually against the Coulomb force between the source charge and the test charge. So since the external force done by us is in opposite direction to the Coulomb force between the source charge and test charge, we are using the negative sign here. So this force is actually represented by Q into capital E. That is, whenever you keep a charge in an external electric field, the force experienced by the charge is given by Q into capital E. So here the test charge is Q prime. So the external work is given by minus Q prime into E. So the change in potential energy is now given by this equation here. Instead of F external, you have to substitute minus F Coulomb. So here minus Q prime and integral vector E dot vector dr. So this is the difference in potential energy. Okay, difference in potential energy between the points P and R, that is given by this equation, minus Q prime into integral E dot R. Now this is the difference in potential. Now what is the difference in potential energy? This is the difference in potential energy that is represented by capital U. Now what is the potential difference per unit charge? So you have to note these terms carefully. This is the potential difference, and what we have discussed till now is the potential energy. So the difference in potential energy between the points P and R is given by this equation. And now the difference in potential between these 2 points P and R is given by dividing this equation by the test charge. Okay. The potential difference means you have to divide the potential energy by the test charge value. That means the work done per unit charge. Okay, what you will get is the work done per unit charge. So here I am dividing the change in energy or difference in potential energy by the test charge value. Then what will happen? This equation gets modified like this. Okay, when you divide this equation by Q prime, this Q prime will vanish. So you will get this term minus integral E dot dr, and the integration limits are R to P. So this is the electric potential difference between the points P and R. So U is the symbol used to denote the potential energy in electrostatics, and V is the symbol used to denote the electric potential in this topic, that is electrostatics. So here the difference in potential between the 2 points P and R is given by delta V. So that is delta U divided by Q prime. That is the potential difference in potential energy per unit charge. That is actually the potential difference represented by delta V. So delta U by Q prime equal to minus E dot dr. Okay, the integration limits are R to P. So this is the meaning of electric potential and electric potential difference. Okay. So now we are going to define the electric potential actually. So it is nothing but the work done. Okay, work done by an external force to bring a unit positive charge with constant velocity. Okay, as you can see in this slide. So electric potential at point P is nothing but the work done by an external force to bring a unit positive charge with constant velocity from infinity to the point P in the region of external electric field. What is the meaning of this statement? Okay, so for that we have to go back to slide number 1. So here actually we have taken the reference point as capital R. Instead of this, when you bring this test charge from infinity, okay, when you bring the test charge from infinity to this point P, what is the work done by you? And the test charge which you are bringing should be 1 coulomb charge. Okay, so that's what the electric potential is all about. And here you see this is the work done to bring a unit positive charge. That means the charge value of that test charge is actually 1 coulomb, and you have to consider the reference point as infinity instead of R. Okay, infinity instead of R. So at infinity the potential is actually 0. Why it is 0? At infinite distance from the source charge, you won't be experiencing any electric field due to the source charge. So you don't have to do any work against the electric field. That means you won't face any repulsion from the source charge because your test charge is at infinity. It is at infinite distance. That means the source charge won't be having any influence at the point of infinity. So V infinity equal to 0. That is the work done per unit charge at the point of infinity is 0. So at the point P, what is your potential? That is given by minus integral infinity to P E dot dr. So this is the equation for finding the electric potential at the point P. So minus integral infinity to P E dot dr. So SI unit of electric potential is nothing but volt, and its dimensional formula m power 1 L square T power minus 3 and I power minus 1. Okay, this is actually I. Okay, I power minus 1. Okay, right. And moreover, this electric potential is not a vector quantity, it is a scalar quantity. Okay, it is a scalar quantity. So the value of this potential may be positive, negative, or it may be even 0. Okay. So now the electric potential due to a point charge, actually we have given the integral form of the electric potential in the previous slide. Okay, here I have given you the integral form actually. So this is the integral form to calculate the electric potential at the point P. Okay, but when you apply this integral and when you proceed further with the calculation, you will be getting this expression in this slide. So that is the potential due to charge Q at the point P is given by V equal to Q by 4 pi epsilon naught into R. Okay, so you can see this is the expression V equal to Q by 4 pi epsilon naught R, and the electric potential is inversely proportional to the distance. So this is the graph between the distance R and electric potential V. Okay, you can see the electric potential value is actually decreasing with an increase in the value of distance r. Okay, so the potential due to a point charge q at the point P is given by V equal to q by 4 pi epsilon naught into r. This is the value of electric potential or electrostatic potential at the point P due to the charge q. Okay, right. So then here also we can apply the superposition principle. So here you see there are n number of charges. So this is q1, this is q2, this is q3. So like that, what you can do is you can take n number of charges. The n can be 100, 200, 150, 300 or any value. Okay. So you have more than one charge in space like this, q1, q2, q3, and you have a point P, okay, which is at a distance of r1 from q1, r2 from q2, r3 from q3, and rn from qn. That means the point P is at different distances from the different charges. So in that case, how will you calculate the total electric potential at this point P due to the presence of all these charges from q1 to qn? What is the net electric potential at this point P? Okay, due to the presence of all the other charges. So here you have the different distances. What you have to do is you have to calculate the electric potential at this point P due to the presence of this charge Q1. After that, you have to calculate the electric potential at point P due to the presence of the charge Q2. So like that, you have to calculate the electric potential due to each point charge, and then you have to go for summation. Okay, so here also the superposition principle is applied, as we have discussed earlier during the our discussion on Coulomb's law and electric fields and all. Okay, so for Coulomb's law also the superposition principle can be applied, and for electric field also the superposition principle can be applied. What you have to do is here, in order to find out the net electric potential at this point P due to all the other charges, you have to go for summation like this. Okay, so P equal to 1 by 4 pi epsilon naught sigma I equal to 1 to n qi by ri. That is 1 by 4 pi epsilon naught is constant. The general equation is electric potential due to the point charge, that is 1 by 4 pi V equal to 1 by 4 pi epsilon 0, that is q by r. That has been mentioned in the previous slide. And here, when you have an assembly of charges, you have to find out the net electric potential by this summation. Okay, here also you are applying superposition principle, right? So in order to illustrate this, we have a numerical problem here. Okay, so the 2 point charges, 2 microcoulomb and -4 microcoulomb, are situated at points -2 meter, 0 meter and 2 meter, 0 meter respectively. That means you have 2 microcoulomb at -2, 0. So which means you can see here. So let me write that now. So here you see the 2 microcoulomb is present here. Okay, the 2 microcoulomb charge is present here, and the -4 microcoulomb charge is present at this point, that is 2, 0. Okay, and what we have to do is we have to find out the electric potential at point C. The point C is here. It is situated at a distance of 4 meter from origin, that is 4, 0. You have to find out the net electric potential at this point C, which is situated at 4 meter, 0 meter, and also at the point D, which is situated at 0, root 5 meter. 0, root 5 meter means this point lies along the y-axis. Okay, so what we have to do is we have to apply the superposition principle and calculate the electric potential at points C and point D. So whenever you have to find out the electric potential due to assembly of charges, so you have to go for superposition principle. So VC equal to VA plus VB. Okay, that means electric potential due to charge at the point A and electric potential due to the charge at point B. You have to find out both the potentials and you have to go for summation. Okay, so here at the point A you have 2 microcoulomb. And what is the distance between this A and this C? Okay, can anyone tell me what is the distance between this point A and point C? Because we have to substitute R. Okay, we have to substitute R because the electric potential due to a point charge is given by V equal to 1 by 4 pi epsilon 0 Q by R. Okay, R is the distance. So here I need to calculate the electric potential due to the point charge A at the point C. Now, can anyone tell me what is the distance between this point A and point C? Can anyone tell me what is the distance between this point A and point C? You can unmute yourself and you can talk. Students, you can unmute yourself and you can talk. What is the distance between this point C and point A? Can anyone tell me? Students, can anyone tell me the distance between this point C and point A? It is actually 6 meter because from here to here, okay, from here to here it is 4 meter. Okay, this is 4 meter from here to here, and from here point A to this origin it will be an additional 2 meter. Okay, so this is an additional 2 meter, so totally 6 meter. So here I have to apply 6. Okay, and potential due to the point charge here minus 4 microcoulomb. So this charge is at a distance of 2 meter from this point C. Okay, so from here to here it is 2 meter. From here to here it is 2 meter. So here I have to apply 2. Okay. So here I have to apply 2. So this is 2. And now you have a K as common and 2 microcoulomb by 6 minus 4 microcoulomb by 2. Okay. So taking K as common, you have to take LCM 6, that is 2 microcoulomb minus 3 into 4, that is 12 microcoulomb. So this is K 2 minus 12, that is 10 microcoulomb divided by 6. Okay. We all know the value of K, that is 9 into 10 power 9. So 9 into 10 power 9. So within the bracket, you will be having minus 10 into 10 power minus 6. So minus 10 into 10 power minus 6 divided by 6. So you can cancel out these terms. This will be 2. Okay. And further you can simplify, it will be 1 by 5. Okay. 1.5 actually. 1.5. So you have minus 1.5. Okay, minus 1.5. So here it is minus 1.5 into 10 power. So this is 10 power 9. This is 10 power minus 6. So that will be 10 power 3. So minus 1.5 into 10 power 3 volt. So this is the electric potential due to the two charges at the point C. Okay, due to the two charges at the point C. Do you all understand? Do you all understand this solution for this problem, students? Do you all understand this? Students, can you hear me?
Yes, sir.
Do you all
Yes, sir.
understand this solution?
Yes, sir. Yes, sir.
Okay, that's fine. That's fine. Right. Now, similarly at the point D, okay, similarly at the point D, you can calculate the electric potential using the superposition principle. Okay, using the superposition principle. So before that, I have to actually erase all these annotations. So, okay, then only you can understand the next part of this problem. Okay, next part of the solution for this problem. Otherwise, the annotations will be disturbing to you. So here you have 2 microcoulomb. So 2 microcoulomb. So at this point D, you have to find out the electric potential due to point A, due to charge at the point A. Okay. So due to actually I can straight away apply all the values, I think. Okay. So now VD, okay, VD equal to, so what is the value of Q here? That is 2 microcoulomb. So before that, you have to apply K into 2 microcoulomb divided by R. Okay, divided by R. So what is the value of R here? R is now actually the distance between this point A and this point C. Okay. How will you calculate the distance? You can apply the Pythagoras theorem. Okay. This is a right angle triangle. This is the right angle triangle, and you only need the distance between this point A and point B. Okay. So how will you calculate that? So that will be square root of, I have to so here it is root of 2 square plus root 5 square. And due to the charge minus 4 microcoulomb, so that will be plus K into minus 4 microcoulomb divided by, here also it is 2 squared, okay, root of 2 squared plus root 5 squared. Okay. So here I am taking out K as common, and also the square root terms as common. Okay. Root of 4 plus 5 into 2 microcoulomb minus K into 4 microcoulomb divided by root of 4 plus 5. Okay. So you can take k by 3. This root of 4 plus 5 is actually root 9. That is 3. Okay. K by 3. You can take it as common. Within the bracket 2 microcoulomb minus 4 microcoulomb. So that will be k by 3 into minus 2 microcoulomb. So k is nothing but 9 into 10 power 9 into minus 2 into 10 power minus 6 whole divided by 3. So when you cancel out these terms, it will be 3. Okay, 3 into minus 2, that is minus 6 into 10 power 3 volt. Minus 6 into 10 power 3 volt. So this is the net potential at the point D due to the charges. Okay. So this is minus 6 into 10 power 3 volt. Do you all understand this problem, students? Do you all understand this?
Yes, sir.
Yes. So thank you so much for your reply, student. If at all you have any doubt in the solution, you can unmute yourself and you can ask during the class. Okay. Right. Now we are moving on to the next thing. Okay. Potential due to an electric dipole. Potential due to an electric dipole. So here you have a dipole. Okay. This is minus q and this is plus q. Okay. So this is minus q charge and this is plus q charge. This is a dipole. The total distance between these two charges is 2a, and this is half of the distance a. This is another half of the distance a. Okay. You have a point P at a distance of r from the center O. Okay. And this point P is at a distance r from O, and the line joining this point O and this point P makes an angle theta. Okay, makes an angle theta. Okay, you can also take theta to this side also, no issues. So when you take theta on this side, then also no issues. So the electric potential due to this dipole is given by V equal to P cos theta by 4 pi epsilon naught r square. Okay, so this is the electric potential due to this electric dipole. This is the general expression, and along the axial line, when you have this point P, okay, on the side of this charge minus q, so when you take theta here, okay, when you take theta here, it will be 180 degree. Okay, it will be 180 degree when the point P lies on this side. Okay, when point P lies on this side, so it will be cos 180, that will be minus 1. So here you will be having minus P by 4 pi epsilon naught r squared. When the point P lies on this side, you will be having P by 4 pi epsilon naught r squared. When the point P lies on this equatorial line, the theta will become 90 degree. So the potential will be 0. Okay. So this is the electric potential due to an electric dipole. Okay. So very simple equation this is. Of course, the derivation is a little bit lengthy, but we are not bothered about the derivation here. We need to understand the final result only. The next thing is the relation between electric field and electric potential. So here you see E equal to minus dV by dr. Okay, this is the relation actually. E equal to minus dV by dr. So this is the relation between electric field and the potential, minus dV by dr. So this minus dV by dr is nothing but the potential gradient, okay? The potential gradient, and when you take the gradient of this potential with respect to the distance and you apply the negative sign, you will be getting the electric field. And when the potential is given as functions of x, y, and z, then your electric field will also have three components, x, y, and z. So the x component of electric field is given by Ex equal to minus dV by dx. Then Ey equal to minus dV by dy. And Ez equal to minus dV by dz. Okay, like this you can do. These are the components of electric field. When your potential is given as functions of x, y, and z, you can do like this and you can find out the electric field. So the net electric field is actually given by this equation. Okay, this equation. So E equal to minus dou V by dou x I cap minus dou V by dou y j cap minus dou V by dou z k cap. That is, the electric field is written in terms of the components. Okay. So here, instead of the full complete differentiation, we are actually applying the partial differentiation dou. Okay. Vector E equal to minus dou V by dou x I cap minus dou V by dou y j cap minus dou V by dou z k cap. This is the net electric field. This is the relation between electric field and electric potential. Now, we have a numerical problem here. Charges of 10 by 3 into 10 power minus 9 coulomb are placed at each of the four corners of the square of side 8 centimeter. The potential at the intersection of the diagonals is given by, okay, you have charges. All the charges are equal. That is 10 by 3 into 10 power minus 9 coulomb. They are placed at the four corners of the square. The side of the square is 8 centimeter. Okay. The side of the square is 8 centimeter. So A is equal to 8 centimeter. A equal to 8 centimeter. Now we have to find out the potential at this point. Okay. The intersection of the diagonals. The potential at this point. So let me take it as so here I am actually marking these things, these corners as A, and this corner as B, and this corner as C, this corner as D. And this point of intersection of the diagonal I am taking as O. Okay. So I have to find out the total potential at the point of intersection of the diagonals. So here also the potential will be due to the four charges. Okay. Of course, all the four charges are equal in sign and magnitude, equal in sign and also magnitude as well. But the total potential at this point O, okay, the total potential at this point O is given by the potential due to the charges at the four corners. Okay, the potential at the four corners due to the charges at the four corners, and here we have to find out the potential at this point. In that case, we need to know the distance between the charge at this point A and this point O. That is, whenever you need to apply the formula V naught equal to, let me take VA plus VB plus VC plus VB. Okay. So here K into Q by R plus K into Q by R plus K into Q by R plus K into Q by R. So since all the charges are equal, and of course since it is a square, the distance AO, BO, CO and DO all are equal. Okay. So all the distances are equal and I am taking them as R. Okay. Since it is a square and you have the point of intersection of the diagonals as O, and the distance between the charges and the point of intersection is equal. So I am using small r. Okay. 1 second. Okay. So now we have to find out the potential. How we are going to do that? We need to know the distance AO. Okay. The distance AO, how we can calculate? That is AO is actually the half of the distance AC. Okay. So the AC squared is equal to AB squared plus BC squared. So AB is A, so A squared plus A squared. This will be 2A squared, that is AC squared. And when you need AC, what you should do, that is AC equal to root 2A. Okay, it is root 2A. So since AO equal to AC by 2, the AO is given by A by root 2, because this root 2A divided by 2, then you will be getting A by root 2, that is half of the diagonal length. So this A by root 2 is nothing but the R value here. Okay, A by root 2 is the R value here, and it is same in all the cases. So now you can apply the R value and the Q value and you can find out the total potential. So for that, let me erase all these things so that I can write a few sentences here. Okay. So since all the potential values are equal, the total potential is 4 times the potential due to the single charge. So V at this point O equal to 4 into 9 into 10 power 9 into single charge, that is 10 by 3 into 10 power minus 9 divided by A by root 2. A by root 2 means A is the side of the square, that is 8 centimeter. So 8 into 10 power minus 2 divided by root 2. Okay. So you can take root 2 to the numerator and this 3 to the denominator. You can do like that. So let me erase these things also. So that I can write a few things here. So this potential VO equal to 4 into 9, that is 36, 36 into 10, 360. 360 into root 2 into 10 power 2. Okay, I am actually simplifying this. Here you have 10 power 9 and this 10 power 9 and this 10 power minus 9 will be cancelled out. And 9 into 4, 36, 36 into 10, 360. This 10 power minus 2 I am taking to the numerator, and this root 2 will also be taken to the numerator. Okay. So this 10 power minus 2, when it is taken to the numerator, it will be 10 power plus 2. and this root 2, when it is taken to the numerator, it is root 2 only. Okay, so divided by 8 into root 3, 8 into 3 actually, 8 into 3. Now you can cancel out all these things. So this is 8 and this is 3 you have. You can cancel out like this. 2 times, this will be 90 times. Okay, and this will be 30 times. And this will be 15. Okay, so 15 into 10 power 2 into root 2. That will be 1500 root 2 volt. This is the potential value at this point of intersection of the diagonal, and that is option B. Okay, that is option B. Okay, that is option B. 1500 root 2 volt. Is it clear to you? Anyone having any doubt? Students, is it clear to you? Do you all understand the solution for this problem?
Yes, sir.
Yes. Thanks for your response. Okay. So if it is clear, then we shall move on to the next slide. Before that, I have to clear all these annotations. Otherwise, it will be disturbing to you to view the next slide. Okay. Then the next thing is equipotential surface. As you can see from the name itself, equipotential. That means the potential is equal. So when you see that the potential is the same at all points on a surface, that is called equipotential surface. Okay, when you have a surface and in that surface, when you have the same electrostatic potential at each point, then that is called equipotential surface. Now, yes, now whenever you have an equipotential surface, then no work is needed to move a test charge over an equipotential surface. Okay, no work is needed to move a test charge over an equipotential surface. How did we arrive at this result? Because W equal to Q into delta V. Okay, so let me change the pen here. So W equal to Q into delta V. This is the equation. So W equal to Q into delta V, and of course W can also be written as U. So U equal to W equal to Q into delta V. That is the work done. Q into delta V. So delta V means the change in potential. Since here in an equipotential surface, delta V equal to 0. Then the total work done will be 0 into Q, that will be 0. Okay. So the total work done to move a test charge in an equipotential surface is actually 0. Then the next point about the equipotential surface is they are drawn such that the electric field is perpendicular to it everywhere. Okay, the equipotential surfaces are usually drawn. Okay, so once again, let me clear this annotation. Okay, so that I can show you the next slide. So here, when you draw the equipotential surfaces, you should draw such that the electric field is perpendicular to it. For example, when I take a positive charge, the equipotential surfaces for these positive charges are nothing but concentric circles. Okay, concentric circles means from this charge you will be having one circle with a radius R1 and the next circle with radius R2. And on all these circles, okay, whenever you take two different points in the same circle, the potential value will be same. And moreover, when you draw the electric field lines, the electric field lines will be perpendicular to the equipotential surface. So usually we draw equipotential surfaces like this only. So that's what it has been given here. In a given region, equipotential surfaces are drawn such that electric field is perpendicular to it everywhere. Okay. The next point is the spacing between the equipotential surfaces enable us, okay, to identify the regions of strong and weak fields. To identify the regions of strong and weak fields. Okay. So how it is possible? How can we identify the strength of the field from the spacing between the equipotential surfaces? So that thing I can show you, that is E equal to minus dV by dr. Okay, E equal to minus dV by dr. So this E is now proportional to dr, inversely proportional to dr, because there is no change in potential. So from the distance you can easily identify whether it is a strong or weak field. Okay. The next point is two equipotential surfaces never intersect each other, because once they intersect each other, at the point of intersection you will be having two different potential values at the same point, which is impossible. So this point is similar to the properties of electric field lines. So electric field lines never intersect each other. So similarly here, equipotential surfaces never intersect each other. Okay. Then here you have electrostatic potential energy. And what is the meaning of this? So when you have a system of charges, okay, like this is an example, Q1, Q2 and Q3. When you have a system of charges like this, what is the work done by you to assemble all these point charges in space? Okay, the total work done by you, or you means actually the external agency. So whenever you want to assemble a system of charges, then you have to do some work. That work done is actually the potential energy, electrostatic potential energy. That means when you want to assemble the charges in the form of triangle here, you have to bring these charges from infinity. At the same time, you have to overcome the repulsive forces due to the presence of other charges as well. So you have to overcome the repulsive or even the attractive forces due to the presence of other charges, and then you have to bring these charges from infinity and assemble here. So for that you need to do a work. That work done is actually the potential energy. That potential energy for this system of 3 point charges, here it is shown like this. Okay, U equal to 1 by 4 pi epsilon naught Q1 Q2 by R12, Q1 Q3 by R13, Q2 Q3 by R23. That means here you can see R13 is the distance between first charge and third charge. R23 is the distance between second charge and third charge. R12 is the distance between first charge and second charge. So U equal to 1 by 4 pi epsilon naught, and then you have to take the pairs of charges Q1 Q2, Q1 Q3 and Q2 Q3, and you have to go for summation. So this is the potential energy for system of 3 charges. When you have a system of n charges, you can take this general formula 1 by 2 into 1 by 4 pi epsilon naught and double summation. Double summation, since you are taking a double summation, there is every possibility to take the same pair twice. Okay, when you take the first charge and second charge, and after that you will be taking the same pair again, there's every possibility. So they actually divide this summation by 2. Okay, then summation, inside the summation you are having Qi Qj by Rij. Okay, this form is actually similar to this thing. Okay, this Qi Qj by Rij, that is the general form. and this is the potential energy for a system of n point charges. Okay. So all these equations are important for your numerical problem solving. And the next thing is relation between potential energy of a charge and electric potential. As I have told you little while ago, that is W equal to Q into V. Here you have U equal to Q into V. This is the relation between potential energy of a charge and electric potential. U equal to Q into V. And the last topic of today's class is that you have a source charge here, and you have two more charges, Q1 here, Q2 here. You have a source charge here. This source charge can be taken as an external electric field, and these two charges, Q1 and Q2, are considered to be placed in the electric field of this source charge. So this source charge produces its own electric field, and moreover, you have to do some work to assemble this Q1 and Q2 here also. So what is the total potential energy of this system of charges in this external electric field? That is given by U equal to 1 by 4 pi epsilon naught Q1 Q2 by R plus Q1 V1 plus Q2 V2. This is the total potential energy of the system of these charges in an external electric field. Okay. So this is the expression for it. And you need to remember all these equations and the formulas so that you can have a good command over solving numerical problems in physics. So you need to remember all the equations and formula. Okay, this will be very helpful to you. And with this, I am completing my session today, and we shall keep it this much for this session, and we can continue our discussion in our next class. If you have any doubts, you can ask now. If you have any doubts on the topics, whichever we have considered today, you can ask me.
No doubts from my side, sir.
Okay, do you all understand the concepts very well?
Yes, sir.
Okay. Thank you so much, students.
Thank
And
you, sir.
let us continue our discussion in our next class. Okay.
Thank you, sir. Children, join in chemistry link. Leave this meeting.